We are going to talk about Tomasulo's algorithm. But first, I'd like to begin with a story. This happened several years ago when I took my daughter to the commissary on a shopping trip. Now, if you've ever been to a commissary, you've probably seen the line that snakes back and forth in front of the registers, as if paying for groceries were a ride at Disney World. But on this particular day, not only did the line zigzag in front of the registers, but it also ran along the entire front of the store, down the aisle toward the back, and even all the way to the refrigerated meats in the back of the store. Now, my first thought was to simply leave. No groceries were going to be worth a wait like that. However, my daughter was just getting to the age when she was old enough to push a shopping cart, so I had an idea. I would put my daughter at the back of the line and tell her to be very careful not to hit the woman in front of her. Then I walked up and down a couple aisles and put some groceries in the cart. Then as she inched along in the line, I was going up and down the aisles, grabbing groceries. And this continued until finally she was almost at the head of the line, just as I was grabbing a carton of ice cream out of the freezer. It could not have been timed any better. Looking back, I realized this is not unlike Tomasulo's algorithm. Had I been by myself, I would have first had to get all the groceries in my cart and then have to wait in line. But we were able to do an out-of-order execution. That is, we were able to start the second task, waiting in line, before the first task, grocery shopping, had been complete. So let's take a look at the architecture on a chip that employs Tomasulo's algorithm. As on any other chip, there is an instruction queue where instructions are loaded for execution, along with some floating point registers. There are also some buffers used to buffer load and store operations. These buffers use address registers and an address unit that can be used to calculate address offsets. Our example will show how these work in just a few moments. These operations are fed into a memory unit that is responsible for reading or writing the data, which hopefully, more often than not, happens in the chip's cache. There are also reservation stations for arithmetic operations. In this example, we have 5 reservation stations. Each reservation station will need to get an operation from the instruction queue, along with the associated operands from the floating point registers. Once everything needed for the operation to occur is in the reservation station, it goes into an ALU. In this example, 3 of the reservation stations go into an adder, while the other 2 go into a multiplier. There are actually 3 adders and 2 multiplying ALUs on this chip, one dedicated to each reservation station. Similarly, there are 3 memory units on this chip, one for each of the load buffers. Lastly, there is a common data bus, where the output from the ALU operations and the load and store operations are broadcast. As we break down a short example, you'll see how this bus is used. Now we're ready to work through our example. Notice how we've put a couple integers into the 2 of the address registers, and there's also some data in one of the floating point registers, in this case, register 4. We are also going to load the next set of instructions from the instruction unit. Before we get underway, we need to state some assumptions. Load, add, and subtract operations will each take 2 clock cycles to complete, while multiply instructions will require 10 clock cycles to finish, and divide instructions 40. Now, it's important to note, these are simply assumptions. It's not like every Tomasulo's chip will take 2 clock cycles for an add and 40 for a divide. But in order to step through an example, we need to know how long an operation would take. So these are the values we've assigned to this particular example. We are also going to track when each instruction was issued and when each one was started. Moreover, we'll track when each operation was finished and when the resulting values are completely written to their destinations. We're going to do this up in the top left corner in a region I may occasionally call the green table. The information on the green table is not on the chip, it's just something included here to help us keep track of what's going on. Nothing has happened yet, which is why we're at clock cycle 0, but let's advance the clock and get underway. At clock cycle 1, we're ready to load this first instruction. The load operand is sent from address register R2 into the address unit, along with the offset of 34, which is found within the instruction. The address unit performs this add, and the resulting value, 76, is put into the load buffer. We will color this load buffer red to show that it is busy. We'll do the same for floating point register F1. It's now busy because it's going to be waiting for the value to be fetched by the memory unit. By the way, how do we know the data is in the cache? That's because of our assumption that a load only takes 2 clock cycles. Were this a cache miss, the operand would probably take 200,000 clock cycles, but I don't think you want to watch a video that long. Good thing that data is in the cache already. In clock cycle 2, the first load command is ready to get underway. The address, once again in this case 76, is fed into the memory unit, which is responsible for fetching whatever data is in that address from memory. We'll mark it red to show that it's busy. But in this clock cycle, we will also issue the second load operation. This one works pretty much the same as the previous instruction, where the address in the load command, which is 45, is put into the address unit, along with the offset in the command, which coincidentally is also 45. The address is calculated and put into another load buffer, which is also marked busy. Lastly, the destination register F2 will be marked as busy, just as happened before. Things really start to get interesting in clock cycle 3. Sure, we're about to issue the multiply command, but first let's get that second load operation into the second memory unit. This memory unit will also go into a busy state. Having more than one memory unit on the chip means we can get the second load operation underway even before the first one is completed, so we're already starting to save some time. But even as this second load operation is getting underway, we will be issuing our next instruction, the multiplication instruction, in this same clock cycle. This works as follows. The multiply operation comes down the operations bus to one of the multiplication reservation stations, which gets marked as busy. The first operand, which comes from F4, is ready to load, and has been since the beginning of this example, so we'll load that via the operand bus. However, the second operand, F2, is not yet ready because that register is still in a busy state awaiting the load. And that's exactly what we'd expect to happen. We can't multiply a number that hasn't been loaded yet, but it's worth noting how we're able to start making progress on this command even before the previous command was finished. In any case, we're going to use this load M2 notation to represent the fact that this command won't be ready to execute until the value has been retrieved by memory unit 2. Finally, we need to mark the destination register, that is, F3, as busy. Now let me back up the clock by just one cycle and emphasize an important point. Everything that occurs in each clock cycle happens more concurrently than I've been depicting it so far. Up until now, I've shown the inner workings as a series of events: fetching the next instruction, filling a reservation station, marking the destination register busy. All this is being shown separately. In fact, though, many of these things will happen more concurrently, so it might look more like this. However, when we animate the activities that way, it's a lot harder to follow everything that's going on. So we'll press forward, dissecting things a bit more piece by piece the way we have been. So let's advance to clock cycle 4. It's been 2 clock cycles since that first load command was started, so that's ready to finish up. The data has been retrieved, and the common data bus lights up. The resulting piece of data is broadcast from the memory unit to any subscribers who are waiting for it. In this case, that's the destination register F1. That value will be loaded here in clock cycle 4, and the register will no longer be busy in the next clock cycle, in this case, clock cycle 5. But that's not all that's happening in clock cycle 4. We still have a subtraction command to take care of. This works much like the multiply operation did, with the operation coming down the operations bus, although this time we are using one of the 3 adding reservation stations, which we'll mark as busy. However, we cannot load either of the operands just yet. F1 is still busy. Remember, that value is just being finished in this same clock cycle, meaning we don't have time to get the data from register F1 yet. Moreover, the other operand, F2, isn't even fetched from memory yet, so we'll be waiting for that load to complete before that operand can be loaded. One more thing we need to take care of before we finish this clock cycle. We need to mark the destination register F5 as busy. That is, no upcoming instruction using F5 should be able to execute until the result of this subtraction has been written into the register. So that brings us to clock cycle 5. Let's begin by looking at what's happening down in our load buffers. First of all, that first load command has now been completely written into register F1, so it's no longer busy. Also, the first memory unit is no longer busy either. So we can free up that resource as well, along with its associated load buffer. But remember that second load instruction, the one that was issued in clock cycle 2 and started in clock cycle 3, it's had enough time to fetch the value from the cache now. So once again, the common data bus lights up, and that value is put into the destination register, that is, into F2. However, something else very interesting is happening here. This value is not only being written to the register, because the register is not the only subscriber to this information. There are 2 reservation stations who are also waiting for this value, and this illustrates an advantage of having the common data bus. We don't need to wait for the value to be written to the register and then one more clock cycle as that operand is moved from that register into the reservation station. Instead, reservation stations can get these values directly from memory via the common data bus. Anyone waiting on this information, be it a register, a reservation station, or a store buffer, can grab that information from the common data bus as soon as it's broadcast from any of the memory units, or for that matter, from any of the ALUs. So let's load that data now. And while we're at it, this load buffer is no longer busy either, so we can free up that resource as well. Now remember, we still have a divide operation to take care of. Because the first reservation station is still being loaded in this clock cycle, it isn't free yet. So we'll use the second reservation station for this operation. Let's mark it busy now. Had there been only one reservation station available, we would stall here. But because there's more than one, we can keep pressing on. So the division operator comes down the operations bus and we can load the first operand, F1. That was a value loaded in the previous clock cycle, just in the nick of time to be ready to be loaded for this instruction. However, if we re-examine our program, we can see that we'll have to wait on F3 until the multiply operation is complete. And since it's just got its operands, it'll be another 10 clock cycles, roughly, before that operand is available. We will have to wait for it to be broadcast over the common data bus before we can start our divide. Now, in clock cycle 6, both of the instructions are ready to go. The data is moved from the reservation stations into their corresponding ALUs, and the multiply and subtraction operations can both commence. We'll add this information to the green table showing when these operations got started. Notice how, much like my daughter and I working in tandem at the commissary, the subtraction operation didn't have to wait for the multiplication operation to finish before it got underway. This is because the chip has more than one ALU, along with the necessary reservation stations that allow the operators to hold their places while waiting for operands to become available. Let's load these operations now and mark the ALUs as busy by coloring them red. We'll also add a note here just to help us keep track of how these calculations are progressing. As those are being kicked off, F2, now that the load has been completely written, is no longer busy and is available for immediate use. Finally, let's update the instruction queue one more time and issue this add command. We'll see this works much like the previous arithmetic instructions. F2, as you remember, is ready for use, so that operand can be loaded right away. But F5, the location of the second operand, is still busy, so we will have to wait for the subtraction operation to finish before we can start this add. You should be able to see what's going to happen here. We now have two instructions waiting for an operand in the reservation stations. But which one will be ready to execute first? That's right, the addition. Because F5, the result of a subtraction operation, is going to be ready long before F3, the result of a multiply operation. So we have an impending out-of-order execution, which is quite exciting, really, since the whole purpose of this video is to demonstrate Tomasulo's algorithm. What's going to happen in clock cycle 7? We have no more commands in the instruction unit, and nothing's ready to come out of the ALUs onto the common data bus, and no instructions were finished in that last cycle, prompting us to remove a busy status. So nothing much happens here, except the ALUs continue to hum along. However, in the next clock cycle 8, our subtraction command is completed, and you know what that means. The result will be broadcast over the common data bus, and the result will go to two places, F5, which is where it was supposed to go as per the instruction itself, and also reservation 2 over on the add side, because that add command is subscribed to the same information. Let's update the green table now before we move on to clock cycle 9, which is the last clock cycle in the video. Here in clock cycle 9, the first ALU adder is no longer busy, having just finished in the previous clock cycle. We can also clear out the first reservation station because the subtraction is now complete. And the same is true for register F5. However, the command in reservation station 2 is now ready to go. So it's time to switch second ALU adder to the busy state. And this sets up our first true out-of-order execution. So now you've seen how the algorithm works. It's not unlike having someone get in line for you while you're picking out shampoo, tomato soup, paper towels, and whatever other items you'll need for the week.